When we hear the word emptiness, we imagine a silent void, a place utterly stripped of matter, energy, motion, and meaning. A space between stars where nothing happens and nothing exists. For centuries, this was how humanity understood the cosmos, a vast, black stage on which galaxies and planets merely float, separated by an infinite, barren desert. But modern physics paints a very different picture. What we once believed to be nothing is, in truth, one of the most dynamic and mysterious entities in the universe. The vacuum, the so-called emptiness between particles, is not empty at all. It is a restless quantum ocean, alive with invisible waves and spontaneous fluctuations. Even in the deepest silence of intergalactic space, fields vibrate, virtual particles appear and vanish, and energy pulses in patterns no human senses can detect. At the heart of quantum mechanics lies a profound revelation: the void is never truly void. The uncertainty principle forbids absolute stillness. Every point in space must fluctuate, must shimmer with zero-point energy, must generate and annihilate virtual particles in an endless dance that lasts only fractions of a moment. Emptiness, instead of being the absence of reality, becomes its foundation, the stage, the engine, and the background hum of existence. This paradox makes the study of vacuum one of the most important pursuits in physics. Understanding the quantum void helps us understand how particles behave, why atoms exist, and how forces emerge. In cosmology, vacuum energy determines how fast the universe expands, shapes the fate of galaxies, and may even define the ultimate destiny of space-time itself. The dark energy accelerating cosmic expansion may simply be the energy of the vacuum writ across the universe. And at the smallest scales, the structure of the vacuum dictates the behavior of fields that permeate reality, including the Higgs field, which gives particles their mass. Emptiness is not empty. It is a hidden architecture, a sea of fluctuations, a reservoir of energy, a canvas upon which the universe paints its laws. In the deepest silence of space lives an infinite number of events. This film begins in that silence, and reveals the astonishing physics of the quantum void. The story of the universe begins in fire, but it may end in absolute cold. If current measurements are correct, dark energy is slowly and relentlessly pushing the cosmos apart. This mysterious pressure, woven into the very fabric of space-time, accelerates the expansion of the universe with every passing epoch. As a result, galaxies drift away from each other faster and faster, carried outward by a stretching space that never stops expanding. In the distant future, this acceleration reshapes the night sky. The galaxies we see today, spirals, ellipticals, dwarf companions, will slip beyond our cosmic horizon, their light forever unable to reach us. The Milky Way will become an island floating in a vast, empty sea. Over unimaginable timescales, even that island will change. Star formation will slow as the cold interstellar gas is used up or expelled. The vibrant glow of newborn stars will fade, leaving only aging red dwarfs and the quiet embers of stellar remnants. Eventually, star formation will cease entirely. No new suns will ignite. The existing stars will burn out, one by one, until the universe becomes a graveyard of white dwarfs, neutron stars, and black holes. The energy output of the cosmos will drop with each dying ember, and the temperature of space will creep ever closer to absolute zero. Heat death is not a catastrophic collapse or a cosmic explosion. It is the slow settling of the universe into its final equilibrium, a state of maximum entropy, where energy is spread so thinly and evenly that no structure can form and no process can occur. Entropy, the measure of disorder, reaches its peak not in chaos, but in uniformity. When everything is the same everywhere, nothing can change, nothing can evolve, nothing can happen. On these timescales, trillions upon trillions of years, even black holes will not survive. Through Hawking radiation, they will evaporate, shrinking until the last whisper of energy fades into the dark. The universe will remain, but only as a cold, formless expanse of thin radiation and dormant matter. No light, no heat, no stars, no galaxies, only silence. This end is not dramatic. It is a dimming, a cooling, a gradual softening of existence until the cosmos becomes a uniform, motionless shadow. A universe that began with brilliant creation ends not with an explosion, but with a whisper, the quiet fading of all things into eternal stillness. Heat death is the ultimate cosmic winter, a fate governed not by violence, but by the slow exhaustion of everything that once made the universe vibrant. There exists a possible fate in which the universe does not drift into eternal cold, but instead returns to the fire from which it emerged. This scenario begins with a single change. Dark energy, the mysterious force driving cosmic acceleration, weakens or reverses. If its strength fades over cosmic time, gravity, the oldest and most persistent of forces, will slowly reclaim its dominance. The expansion of the universe will begin to slow, like a stone thrown upward losing momentum under Earth's pull. At first, the change would be imperceptible. Galaxies that once drifted apart would gradually decelerate. Cosmic distances would stop growing. Then, in a profound turning point, expansion would halt entirely. The universe would reach its maximum size. After that moment, everything changes. Gravity would begin pulling the cosmos inward. The universe would start to contract. Galaxies would creep closer together, their motions reversing the outward push of billions of years. Over immense timescales, clusters would merge, superclusters would collapse, and the cosmic web itself would fold inward like a shrinking tapestry. As space contracts, its temperature would rise. Background radiation, once stretched thin by expansion, would become increasingly energetic. The night sky would grow brighter, not darker. More galaxies would come into view as they rushed toward one another. Collisions would become common. The merging of spiral galaxies, the violent interactions of star clusters, the coalescence of central black holes into titanic singularities whose gravitational waves shake the fabric of space-time. Stars would be torn apart by immense tidal forces. Shockwaves of radiation would sweep through collapsing regions. Black holes would collide, forming even larger gravitational giants. The cosmos would transform from the cold emptiness of its middle age into a furnace of compression and chaos. As contraction accelerates, space becomes hotter and denser. All matter is pushed into closer proximity until the universe resembles its earliest moments, a seething plasma of fundamental particles. Temperatures soar beyond anything stars could ever produce. Quantum fields saturate the cosmos. Light loses meaning as distances shrink toward zero. In the final moments, everything collapses into a single radiant point, a singularity. A mirror image of the Big Bang, but in reverse. The Big Crunch. Some theories suggest this singularity might not be the end at all. Instead, it could be a doorway, a point of maximum density that rebounds into a new expansion, a new Big Bang, creating a new universe with new laws, new constants, new forms of matter. In this view, the cosmos becomes cyclical, an endless sequence of births and collapses, universes rising and falling like the inhale and exhale of a cosmic breath. Whether the Big Crunch is an ending or a beginning, it remains one of the most dramatic possibilities in cosmology, a universe that ends not in silence and cold, but in fire, pressure, and rebirth. There is a version of the universe's future in which the force tearing space apart does not remain gentle or steady. Instead, it grows. Dark energy, already responsible for the accelerating expansion of the cosmos, could evolve into something far more dangerous. Some theories call it phantom energy, a form of dark energy whose strength increases over time, amplifying the rate of expansion until it overwhelms every binding force in existence. At first, this evolution would be nearly invisible. Astronomers would notice that distant galaxies drift away faster than expected. Over billions of years, the acceleration would intensify beyond anything seen in the standard cosmological model. But the real drama would begin when the growing expansion becomes strong enough to overcome gravity, not just between galaxy clusters, but within individual galaxies themselves. In this scenario, the Milky Way would not be safe. Galaxies would gradually stretch, their stars pulling apart as the very space between them expands with increasing violence. Structures that once seemed eternal, spiral arms, central bulges, massive halos, would disintegrate. The night sky would dim not from collapse, but from distance. Every galaxy would flee from every other at unimaginable speeds, until the universe becomes a scattering of isolated stellar islands disappearing into darkness. But phantom energy does not stop at galaxies. It grows stronger still. Eventually, the expansion becomes powerful enough to break the gravitational bond between stars and their planets. Solar systems decay. Planetary orbits unravel. Worlds drift into cold space, flung away from their stars by the accelerating stretching of the cosmic fabric. And still, the force increases. On even shorter timescales, the expansion overwhelms the forces that hold stars together. Nuclear furnaces that have burned for billions of years would be pulled apart. White dwarfs, neutron stars, even black holes, objects defined by extreme density, would succumb to the relentless expansion of space. No strength of gravity would be enough. Approaching the final moments of the universe, the timeline becomes shockingly brief. In the last minutes, solar systems fall apart entirely. In the final seconds, planets are ripped apart by tidal forces stronger than any gravity they have known. In the last fractions of a second, atoms, the building blocks of matter, lose their integrity. The electromagnetic force, normally so powerful that it binds electrons to nuclei with near unbreakable strength, becomes too weak in comparison to the stretching of space. Matter dissolves. Particles separate. Even the quantum fields that sustain existence begin to fail. Finally, space-time itself reaches a breaking point. The expansion accelerates beyond infinity, tearing the fabric of the universe into disconnected fragments with no past, no future, no continuity. Unlike the heat death or the Big Crunch, the Big Rip offers no rebirth, no cyclic return, no lingering echo of structure. It is the most dramatic of all cosmic endings, a total destruction of everything that can exist. In this scenario, the universe does not fade or collapse. It is ripped apart from the largest scales down to the smallest, until even the concept of space no longer holds meaning. It is the ultimate expression of expansion carried to its absolute extreme. The moment when the cosmos becomes too dynamic, too fractured, too stretched to remain a universe at all. There is a version of the universe's fate that does not rely on gravity, expansion, or the distant cooling of stars. Instead, it emerges from the deepest layers of quantum field theory, the idea that the very fabric of reality may not be in its most stable state. According to modern physics, the vacuum is not simply empty space. It is a field configuration, a sea of energy that determines the rules of the universe, how particles behave, what forces exist, and which constants define the structure of matter. In the Standard Model, there is a possibility that our vacuum is not the true lowest energy state. It may instead be metastable, stable enough to persist for billions of years, but not guaranteed to last forever. If a deeper, lower energy vacuum exists, the universe might one day make the transition. Not through a cosmic disaster, but through a quantum event, a fluctuation that creates a tiny region, a bubble, of true vacuum. This bubble would represent a fundamentally different version of reality, governed by new constants and new laws of physics. It would not be a place compatible with the structures that exist today. Once formed, this bubble would expand at the speed of light. Because nothing can outrun light, no observer could detect its approach. No warning, no signal, no tremor in the fabric of space would precede it. The moment the bubble reached a region of space, that region would instantly transition into the true vacuum. Outside the bubble, the universe as we know it. Inside the bubble, a different universe, alien, hostile, incompatible with matter as we understand it. Within the bubble, the Higgs field could settle into a new configuration, altering the masses of particles. The electromagnetic force could change strength. Nuclear interactions might vanish or become unstable. Even the speed of light could be different. In such conditions, atoms would not survive. Chemistry would cease. The fundamental building blocks of stars, planets, and life would no longer hold together. It is not an explosion, and it is not destruction in the thermal or gravitational sense. It is a redefinition of existence, a rewriting of the rules, a reset of every field that governs the universe. Under this scenario, the transition is silent and instantaneous at the boundary. A bubble only microns wide at birth would grow into a cosmic front, sweeping across galaxies, clusters, and the cosmic web. Entire star systems would never notice the moment of change. One instant they exist, the next they are rewritten into a new quantum reality. Physically, this process is elegant. Emotionally, it is one of the most unsettling possibilities. The universe ends not with fire or collapse, but with a quiet phase transition, a quantum shift propagating at the maximum speed allowed by nature. And yet, there is a strange beauty in this idea. Vacuum decay is also creation. The birth of a new set of physical rules, a new space-time, perhaps a new universe that evolves according to different mathematics. What seems like annihilation from our perspective may simply be the natural evolution of the cosmos into its most stable form. It is a reminder that everything we know, every atom, every force, every constant, rests upon a delicate foundation. The universe appears stable, but its deepest layer may hold a different story, one where reality can transform in an instant. remaking itself without warning. Vacuum decay is not a cosmic catastrophe in the traditional sense. It is something more profound, a fundamental reconfiguration of existence itself. There is a final possibility for the fate of the universe, one that does not end in silence, collapse, or dissolution. Instead, it imagines the cosmos as a system that regenerates itself, using the deepest laws of quantum gravity. In this scenario, the end of one universe becomes the beginning of another. Some modern gravitational theories, such as loop quantum gravity and certain versions of string cosmology, propose that spacetime cannot compress indefinitely. As the universe contracts under its own gravity, or evolves toward extreme densities at the end of its lifespan, quantum effects begin to dominate. These effects resist further collapse, producing what scientists call a quantum bounce. Instead of ending in a final singularity, the universe rebounds. What appears to be an ultimate collapse from one side becomes a new Big Bang from the other. Energy, space, and time re-emerge, expanding outward into a new cosmic epoch. This process forms a bridge between universes, connecting endings and beginnings in a single, cyclical flow. In this framework, our own Big Bang might not have been the first moment of existence, but rather the aftermath of a previous universe collapsing into quantum density. The seeds of our cosmic structure, the distribution of galaxies, the fluctuations in the cosmic microwave background, could carry faint fingerprints from a universe that existed before ours. Some theories extend the idea further. The universe may not cycle as a whole, but may reproduce through black holes. When a massive star collapses and forms a black hole, the internal spacetime might pinch off, creating a separate expanding region, a baby universe, detached from its parent. In this picture, our cosmos could be the interior of a black hole that formed in another, older universe. The event horizon of that black hole would mark the boundary between eons. If so, the universe does not simply die. It transforms. Each collapse becomes the womb of new spacetime. Each end births new beginnings. And every universe that forms may carry different physical constants or laws, shaped by quantum processes that occur during the bounce. This scenario is more than a poetic metaphor. It is a mathematical possibility supported by several frameworks that aim to unify gravity and quantum mechanics. It paints a picture where existence is not a single, linear story but a chain of cosmic epochs, each one giving rise to the next, like beads threaded on an infinite string. In the quantum rebirth scenario, our universe is not a lonely accident. It is one chapter in an endless library of universes, each emerging from the ashes of the one before it. And perhaps, somewhere far beyond the reach of our observations, new universes are already unfolding from the gravitational cores of collapsing stars. The cosmos may not end. It may simply begin again. Beyond the major scenarios, heat death, big crunch, big rip, vacuum decay, and quantum rebirth, there are other possibilities that lie at the edge of our scientific imagination. These futures stem from the simple truth that the universe may contain ingredients we have not yet discovered, forces we have not yet measured, and behaviors we have not yet observed. One such possibility is that dark energy changes over time. We currently treat it as a constant force stretching space, but nothing guarantees its stability. If dark energy weakens, the expansion could slow and shift the cosmic trajectory toward eventual collapse. If it strengthens, even slightly, the cosmos might move toward a gentler or more chaotic form of accelerated expansion, a version of the future that does not fit neatly into our existing categories. Another factor is dark matter, the invisible scaffolding that shapes every galaxy. Its long-term behavior remains a mystery. If dark matter decays over trillions of years, galactic structures may gradually unravel, altering the path toward cosmic equilibrium. If it interacts through forces we have not yet detected, its influence on the geometry of the universe could shift outcomes in ways our current models cannot predict. There is also the possibility of new fundamental forces or particles. Physics is not complete. Our current theories may be only approximations of a deeper framework. The discovery of a new interaction, something that operates only on cosmic scales or at extremely low energies, could rewrite our expectations for the distant future. A subtle long-range force might slow expansion, redirect it, or reshape the fate of matter itself. And finally, the universe may possess a topology we cannot perceive. Space might wrap around itself, curve in higher dimensions, or extend infinitely in ways our observations cannot probe. If the cosmos has a hidden geometric structure, like a torus, a loop, or a multi-connected manifold, its ultimate evolution could follow patterns that lie entirely outside our imagination. In this sense, the future of the universe is not a single path but a landscape of possibilities. Our fate depends on forces we are only beginning to understand, particles we have not yet discovered, and the deep geometry of space-time that remains concealed from us. The cosmos may end in silence, collapse, renewal, or something far stranger, something that awaits us beyond the horizon of current physics. One of the most unsettling possibilities in modern physics is that our universe may not be in its true ground state. Instead, it may be resting in what physicists call a false vacuum, a temporary, slightly unstable configuration of space-time that only appears stable because the transition to a lower energy state has not yet occurred. In this view, everything we know, atoms, forces, chemistry, the very structure of matter, rests on an energy plateau that is not the lowest the universe could achieve. Quantum field theory allows for the possibility that the vacuum has multiple states, like valleys separated by hills. Our universe may be sitting in a shallow valley, while a deeper one lies somewhere below. Under rare conditions, a particle interaction or a quantum fluctuation could trigger quantum tunneling, creating a tiny region, no bigger than a subatomic particle, where the vacuum collapses into its true, lower energy form. This region is called a bubble of true vacuum. The disturbing part is what happens next. Once formed, this bubble would expand at the speed of light, converting everything it touches into a radically different form of reality. Inside, the laws of physics might be completely rewritten. Different particle masses, different forces, different constants of nature. Atoms as we know them could not survive. Chemistry, stars, galaxies, life, all would be erased, not through destruction but through transformation. It would not feel like an apocalypse, because no observer would ever notice it arriving. The bubble frontier moves at light speed, leaving no warning, no sensation, no possibility of escape. But despite its dramatic implications, vacuum decay remains only a hypothesis. It relies on assumptions about the Higgs field and other aspects of the standard model that may be incomplete. Quantum gravity, which becomes relevant at extreme energies, might stabilize the vacuum in ways we do not yet understand. And even if the vacuum is metastable, the timescales involved could be unimaginably vast, far longer than the lifetime of stars, galaxies, or even protons. Ultimately, vacuum instability forces us to confront a humbling idea. The universe might appear calm and predictable not because it is stable, but because its instability lies beyond the reach of observation. Our entire cosmic history may be unfolding inside a temporary state of reality, one that could, in principle, be replaced by something entirely new. One of the most profound questions in modern cosmology is whether the vacuum, the very ground of reality, can evolve over time. We often imagine nothingness as perfectly still, a silent backdrop against which the universe unfolds. But in quantum physics, the vacuum is not an empty stage. It is an active, dynamic medium defined by fluctuating fields and hidden energies. And just as matter and radiation evolve, it is possible that the vacuum itself may change as the universe ages. The energy of the vacuum, what we call dark energy, already shapes cosmic history by accelerating the expansion of space. But physicists do not know whether this energy is constant. It could, in principle, drift, strengthen, weaken, or fluctuate as the underlying fields evolve. In some models, dark energy behaves like a slowly rolling scalar field rather than a fixed constant. Over billions or trillions of years, this field could transform, altering the structure of space-time in ways we have never witnessed. Beyond dark energy, the vacuum might harbor exotic quantum states we have not yet discovered. Quantum field theory predicts higher-order phases of vacuum structure, similar to how matter can exist as solid, liquid, or plasma. These phases might involve unusual symmetries or hidden dimensions, accessible only when the universe becomes colder, emptier, or more diffuse. In such scenarios, the vacuum of the distant future might not resemble the vacuum of today. There is also the possibility of new fields, such as those associated with dark matter or the remnants of inflation. Dark matter may interact with the vacuum in ways we do not yet understand. Its presence could subtly influence the long-term evolution of the cosmic energy landscape. And inflationary theories suggest that the early universe emerged from a particular vacuum configuration, one that may or may not be stable over cosmic time. If the inflationary field still exists in some dormant form, it could reactivate or transition again in the far future, altering the cosmic expansion in radical ways. In the most speculative models, The universe behaves like a quantum object capable of shifting between states. Just as electrons jump between energy levels, the entire cosmos could undergo a phase transition, a sudden change in the vacuum configuration that redefines the laws of physics. This does not necessarily imply destruction or collapse. It could simply mean a transformation in the deep structure of reality, a new chapter in the cosmic story. The farther we peer into theoretical physics, the clearer it becomes. The vacuum is not a static canvas. It is a participant in the evolution of the universe, with a past, present, and possible future. And as the cosmos ages, even nothing may not remain the same. In the end, the greatest mystery of the universe is not the galaxies, nor the stars, nor even the black holes. It is the vacuum itself. The silent, invisible nothing that fills the vast spaces between worlds is not an absence but a beginning, the hidden engine that shapes all cosmic structure. Quantum physics revealed a truth that still feels unsettling. Even the emptiest regions of space are alive with fluctuations, tiny bursts of energy that appear and vanish in less than an instant. These fluctuations were the first architects of the universe. In the earliest moments after the Big Bang, they were stretched across cosmic scales, leaving faint imprints, tiny wrinkles in the newborn fabric of space-time. And those wrinkles became the seeds from which galaxies grew. Every spiral arm, every cluster, every star that has ever burned began as a whisper in the vacuum, a momentary tremor in the quantum void. What we call structure is, in reality, the memory of ancient fluctuations magnified across billions of light years. Without them, the universe would be perfectly smooth, perfectly silent, and perfectly lifeless. This is the paradox at the heart of modern cosmology. The most powerful creative force in the cosmos is not matter, not radiation, not gravity, but the restless energy of nothingness. The vacuum does not simply permit existence, it generates it, sustains it, and shapes its evolution. And so the universe ends with a poetic truth. Between the stars lies not silence, but an infinite creative pulse. Nothingness is not the absence of reality, it is its foundation.